It's free fall with Mr. Ross. Super exciting. Free fall. All right, here. All right, so first question is what is free fall? Don't Google it. Just kind of, what do you think? Is it like this guy over here? Wait, where is he going to go? And boom. Or is it like this? All right, so this is the most common thing that I get when people ask me or when we talk about free fall, is that people immediately mention skydiving. They say jumping out of an airplane is what free fall is. All right, but what free fall actually is when you are falling with only gravity acting on you, meaning no other forces, nothing else. So when you jump out of an airplane, there's more than that. See the clouds? Those clouds are in your way. All that water vapor and all the air around you is actually in your way. So this is not only with gravity. What we really have is a force down, which would be the force of gravity, and we have a force up, which would be, say, the force of air resistance. All right, so here we have, I'm drawing a little picture on the guy, force gravity. So there's the gravity pushing, not pushing, yikes, pulling it down. And then we have this pink vector here, which is totally fair. It's the force of air. Hilarious, okay? So zooming in for some apparent reason. Fun fact, I draw all these and record myself drawing them, and then I voice over later. So sometimes I'm not so sure what I'm doing. All right, so the gravity is pulling you down. The air is resisting you falling. But in this class, we can ignore air resistance because the reality is that for the most part, the air resistance is not going to matter that much for a lot of what we're doing. So if you're, say, dropping a ball from a height of 2 meters, it's going to be negligible, meaning not much of a difference between the time that you would calculate ignoring air resistance and the time that you would very accurately measure with highly sophisticated tools that actually, are the ball is including the air that the ball is actually falling through. Fun. So all of what we do, you will often see neglecting air resistance on there, just like in space. Look at all these arrows. These arrows represent the direction that gravity is pulling stuff. It always pulls stuff towards the center. So if you're an astronaut and you're right here, you're going to follow that arrow. You're going to be pulled down to Earth, towards the center of Earth. If you're an astronaut down here, you're going to be pulled to the center of Earth, from that direction. The Earth is round, folks. So pull stuff in. We are going to live in this neighborhood right here, what's known as close to the surface of Earth. If you're way over here by the moon, things are a little bit different. And the man on the moon, he's always going to be, what is he going to be, smiling? There he goes. He smiles. So we are going to deal with forces that are close to the Earth. So some questions you'll see near the surface of Earth be thrown in there sometime. It doesn't necessarily need to be, but that's where we're going to be. Later on, when we talk about gravity and different things, we're going to be talking about between different planets or far away, because we understand that at some point, gravity kind of gets less, right? We imagine that when we're in space, gravity is less. Sometimes we say there's no gravity, but that is not the case. What I need you to do right now is to look in your reference table and look up the acceleration due to gravity and see if you can find it, see if you can answer this question. There it is. 9.8 meters per second squared. That's what it says in your reference table. Another way to think about an acceleration is always 9.8 or meter per second, meaning it's the rate at which your velocity increases. Okay, so when we have an object that's falling, it means its speed is increasing as a result of that acceleration due to gravity at a rate of 9.8 meters per second. So if you drop something, its velocity starts at 0. So at time 0, its velocity is 0 meters per second. As it falls, it's going to speed up. As it falls down towards the Earth, it is going to speed up. So after 1 full second, your speed is now 9.8 meters per second, because your speed increases as a result of the acceleration due to gravity at 9.8 meters per second every second. So after 2 seconds, it's 19.6 meters per second, and so on. 3 seconds, 4 seconds, and so on. So we can imagine now that we can find all of these different speeds using this acceleration due to gravity. And now that we know about it, we no longer have to give you an acceleration in the problem. So if I put a ball, near Earth, obviously not drawn to scale, otherwise that is a humongous ball. And also, look how big Florida is. Fun. So the ball is going to fall down, obviously. It's going to be released from rest. We're going to drop it. And whenever we say drop it, it means released from rest. So because it is dropped, its initial velocity is equal to 0. Okay, so that's something that we know. It's an example of a problem where I don't have to give you a number, all right? Just like before when we said rest, I don't have to give you that number. It doesn't appear there, okay? And you have to know what that means. All right, let's say we're looking for the speed sometime later, okay, or or the speed after, say, 3 seconds or something like that. Okay, you always know the acceleration due to gravity. Now, again, another number I don't have to tell you. So the acceleration due to gravity is 9.8 meters per second squared. Time, all right, what did we say? We said 3 seconds. Okay, so 3 seconds later, we want to know what the speed is. So again, we look down this column right here. We see we have a VI, an A, a T, and a VF, and we need to figure out what equation we need to do. The time is the only piece of information. It's the only number, I should say, that you will see in a problem like this. So you could be given a problem and only see one number in the problem and asked to find something about it. And you have to know that the initial velocity is 0 because it's dropped. You have to know the acceleration due to gravity is 9.8 meters per second squared. Okay, so we figure out the equation because of the variables that we have. We write it down and we start to substitute into it. All right, so we say 0 meters per second and we say 9.8 meters per second squared is our acceleration, and we substitute in our time. Okay, our time of, 3 seconds. Oh, hold on. We forgot something. Wait. All right, what did we forget? Well, these things are falling down, all right? And we tend to call down negative, all right? We need to define our direction. So if we're calling down negative, then our acceleration needs to be negative. And that'll give us a negative final velocity, which is important, all right? Because we need to be paying attention to these directions all the time. Right now, we're only moving in one direction at a time, but as we start to move this way and that way, we really need to be really careful with our directions. So it's a negative 9.8. So when we substitute that in, we get a negative 29.4 meters per second, which means it will be falling, that ball, no matter what, will be falling at 29.4 meters per second. Down, because of the negative. Here we have a chicken in a tree. Yes, that's a chicken. Yes, it's the worst chicken ever drawn. No, I don't know what's going on with its knees. Yes, it's a lame wing, but whatever. This is a reasonably tall tree. So just as a reminder, 3 meters is about 1 story. All right, so 6 meters would be 2 stories. So this is a tree that's almost a 2-story tall tree, or I guess it would be a 2-story tall tree, and the chicken is almost 2 stories high, so 5 meters. So let's figure out what we can figure out. Let's pick something. Let's say what speed. What speed is the chicken going to be traveling when it hits the ground? And so this chicken is falling, and it's falling in the absence of air resistance. So let's take a look at this. What do we know? Well, in the surface of this problem, we're only given one number, and this one number, this 5-meter number here, is enough for us to solve this question, right? Because we do know a little bit more than what's on the surface here, even though the question only has one number in it, and that one number is the 5 meters. So what do we know? Okay, so let's see if we can figure that out. All right, you back? No? Yes? Maybe you are. All right, so we're gonna write things down in the same fashion that we have before. Zoom out just a little bit here and get all situated. Pretty fancy stuff. You're welcome. All right, so we know the initial velocity. The chicken is going to be falling out of the tree, so its initial velocity is 0 meters per second. Come on. Write it down. There we go. 0 meters per second. Excellent. Okay. We know that we're looking for the final velocity. What else do we know? Well, we know we're not given a time. We know we're not given an acceleration, right? Or are we? Remember that we always know the acceleration because it is falling. And yes, we should define our directions. There's that 5 meters. Now, the chicken is ending up below where it started, meaning our 0 is where the chicken is. And 5 meters is below. So that 5 meters is down. The chicken is being displaced down. So both our acceleration and our displacement need to be negative because they are both vectors that are directed down. So we need to look for our equation. Looks like we already found it. And that equation is VF squared equals VI squared plus 2AD. All right. The rest is math. All the physics is done. We figured out that the chicken is falling and that it's poorly drawn and all the directions and all the numbers associated with the variables. So substituting those values in, we get the following. Look, those negatives, they cancel out. That would be important. Otherwise, we'd end up with a square root that we couldn't solve. Exclamation point. Excellent. All right. So now we also need to remember that we always need to pay attention to these squares. Most common mistake in New York State Regents physics is forgetting to square stuff. So make sure you don't forget. All right, so let's do the math. All right, the next line is going to look like VF squared is equal to what? 2 times 9.8 is 19.6 times 5. Everybody knows is 98. And roughly the square root of 98 is 9.9, right? So it's almost 100. So the square root of that is almost 10. So 9.9 is what going to be. VF is equal to 9.9. Write it down. Come on, past time. There it goes. All right, VF is equal to 9.9 meters per second. And we can box it and we're done, right? Uh-oh, we might be forgetting something. Let's take a look back at the chicken. All right, so there's the chicken. We're going to try another problem. All right, remember that everything down is negative and everything up is positive. So I want you to find the speed the chicken hits the ground in this new and improved 3-meter tree. Here comes the answer. So we get our 7.6, little rounding, 7 meters per second. Super exciting. Oh, we forgot something. Remember, this is the velocity we're talking about. So it is down. It needs to be directed down, which means it needs a negative sign, which means we forgot to do something in that previous problem. Remember, every time you take the square root of something, right? Square root, you're saying plus or minus. All right, so that's really 9.9, right? With the plus or minus sitting out front. Pretty exciting stuff. But it is obviously not going up. Chickens don't fall out of trees and go up because they can't fly. So it needs to be that negative 9.9. Negative is the one you need to choose. SpongeBob, you're welcome. The end.